since we have 40 minutes for 4 challenges, I'm going to give a quick 10 minutes. Can you see this?
Yep, looks good.
Okay, great. So I'm going to give a quick 10-minute pitch on about this challenge that I'm proposing, the meta learning with spikes. And just to give you the idea of what we'd like to do and like to take the discussions over later on Slack and a smaller group who is specifically interested in this. So just reminding you from the tutorial, I think one reason why meta learning is important is to solve problems like this. So remember, if I tell you this, these objects in the red boxes are tufas and find the other ones, you'll have no problem in doing this. And this is something that, a lot of deep neural networks don't come natively with this capacity, and you have to somehow add it, and meta learning is one way to do this. So that's why meta learning is important. But why is it important for neuromorphic engineering? I think there's a real opportunity here. So learning from the very early days of neuromorphic engineering has been a big focus of the engineers and also the chips that are being built. And already now there are a number of neuromorphic projects, including Giacomo's Giacomo Indivi's chips and the Human Brain Project, and also we just heard about the Intel Loihi that really had these capabilities of online learning that is local and in most cases are directly inspired from dynamics of synaptic plasticity. But so far, I mean, all of this has more or less remained as a curiosity, and we're seeing some real practical examples in Loihi with this, with ABR and some of our work as well. But it's not obvious how we can do learning on these neuromorphic chips. And this really relates to some of the points that I raised during the tutorial as well. I'll be reminding them here is that learning on site, so online, is actually something that's extremely hard to do. It violates the very assumptions of statistical machine learning, that your data must be IID, so independent and identically distributed. If it's not, then all hell breaks loose, for example, in the form of catastrophic forgetting. So some tasks that you learned in the beginning just gets lost as you learn other tasks. Deep learning in general is extremely data inefficient, right? We just saw this also with Mike Davies' talk earlier that, for that olfaction example, you need to have many data samples for deep learning to work well. And so one possibility to overcome this is to have some prior knowledge. And of course, meta learning is one way to obtain it. And of course, we can, and we also saw this in Sin Wang's talk. So once you have a physical instantiation where memory is not shared across all these cores, well, you can't really do this data parallel approach where you copy your model over across your chip or hardware. So the real world is basically bat size equal 1. So if you take all of these together, it's a very bad picture actually for doing deep learning online with or in general gradient-based learning online. So this challenge is going towards solving that problem. And there are many ways of solving the problems of online learning. And so again, I mentioned some of these during my tutorial, but what we'll be focusing on during this challenge is going to be the meta learning, which is one possible solution how to overcome the challenges of online learning. And one example of this is on this figure on the right. So this comes from the paper called Model Agnostic Meta Learning, where what you can do is learn a particular instant initialization of your parameters such that adapting your network to a new task is actually just going to take you a few steps, just a small distance away from your original parameter, such that you don't really destroy your previous, so you stay close to this region here, and so you don't lose performance here. And so you don't have catastrophic forgetting. And this is interesting again from neuromorphic implementation, because maybe some of the meta learning aspects can be done offline, say on a GPU or on a Cerebras CS1. but the local learning and adaptation then can be done on the neuromorphic hardware. So what you get there then is a much different picture, where basically the loihi or the neuromorphic hardware does the job of the last mile. Really, it takes you to where you have to reach, and it does a very important job and really justifies the needs for synaptic plasticity on neuromorphic hardware. So that's really why I propose this challenge. So the challenge plan is largely open, but of course, what we need to do, one of the things we need to do is define a proper benchmark. So Omniglot is the typical benchmark that's used. We saw this in Wolfgang Maus's talk. It's a typical benchmark that's used for testing meta-learning. It's like the MNIST of meta-learning, where you have many classes in few instances. So let's define the Omniglot of event-based data. Remember, if you're going to do this with spikes, it makes sense to use some event-based data, or at least convert them in a meaningful way. And the second is, once that we've defined these benchmarks, is to approach these so meta learning, and another name for this I should have mentioned is few-shot learning, and using both classical neural networks as a benchmark and spiking neural networks, and of course mixing of non-local learning and local learning can be really interesting, again, in this idea of pre-training and then post-training. The few-shot learning setup is generally, and I'd like to make a little bit more concrete here. Basically, what you do is that you have a bunch of data sets with labels. That's the meta training data set, and you can meta train your network or pre-train your network there with the training and the testing part. So you do this until you want to meta test your network. And when you do meta test, you basically have a small training set with only a few instances of every class. And then, but you don't have the labels for the testing class. So this is the real kind of, the goal here is to perform well on this box here. Remember that, so I'd like to be clear here that this is specific for classification. The reason why we do this is because we can compare it well and use a lot of the tools that are, and techniques that are available out there. And for us to really get started here, so what I did here as a first benchmark, a first step into this is to build what I call here the double MNIST. So there exists actually a double MNIST data set, and but what we can do is use the Garrick Orchard's neuromorphic MNIST that he recorded with the DVS, and just basically concatenate two digits. And so this way we have 100 classes because we have 10 digits on the left, 10 digits on the right. So this means that we can have 100 different types of classes for the overall network. But the goal for every meta task then is to do, for example, a 5-way classification with these digits here. And the goal of meta testing then would be to generalize this classification to other combination of digits that it has not seen before, for example, 88 or 89. Okay, so that's available on this package that I've created, Torch Neuromorphic. On the channel, there's a few examples of how to just how to generate this data set and get started. It works just like Torch Vision. So this should be, if you're familiar with Torch, it should be pretty easy to get things going here. So that's all I want to say here about the project itself to the larger group here. And so I think we can organize on the Slack channel directly of how to proceed. But whether you're interested in producing the benchmarks or explore the different approaches, I think there's a lot of interesting things we can do and very impactful things, I think, also for the neuromorphic community.
All right, thank you.
Thank you. Okay,
so the next one will be Toby.
Okay. Do you want to stop the recording after each one, or make it all in one lump? I think we'll keep it all together and put a marker in there. Somebody nicely shared my thing. So I'll share my screen here with computer sound, and I'm going to start out with something that means a lot to me. And also to other people who have been at the workshop for a long time. I just want to, this is in memory of Daniel Fasnacht, the guy who's sitting right here, who died after a long illness about 2 or 3 months ago. And he was very much a part of the neuromorphic community for about 6 or 7 years as a PhD student of Giacomo's. He was solely responsible for the complete IT infrastructure of the workshop. And in this picture here, we have Sim Bamford and Ping Wang from Terry's lab, Andrew Cassidy from Quabena's lab and later IBM, Shichi's back here, and a bunch of characters. So anyway, this is for you, Daniel. I miss you very much. Now, I'll go to our topic area challenge this year and just show you these slides. So I want to start out in 2019. We had a topic area. You saw already from Terry this picture. Can you see the slides okay? So we had a topic area on controlling dynamical systems. You see Andreas, you see Rachel and Chang. And I just want to tell you about one piece of work that especially Rachel and Chang did at the workshop on recurrent neural network control of a hybrid dynamical transfemoral prosthesis with edge DRNN accelerator. That's a real mouthful, but what it means is that they is the first time that anybody used a hardware accelerated RNN for real-time control. And it was published in ICRA. And basically what they did was, Rachel had this powered two-motor lower leg prosthetic intended as a prototype for people that lose their lower legs. You know, it's a little bit like people are now using e-bikes. People will eventually use e-legs and they'll charge them up at night and use them all day. But the whole activation patterns of these kind of prosthetics in Rachel's work is done by proportional derivative control that keeps the leg on a particular gait pattern. What they did was they recorded the data from the sensors and the control, and then Chang trained an RNN to replicate what the PD controller could do, and then ran that on the RNN accelerator. And this RNN accelerator is really quite cool because it's kind of a spiking RNN accelerator. It exploits temporal sparsity so that it reduces the memory access a lot of the fully connected network. Anyway, they managed to run this thing in hardware at the workshop, and I thought that was a wonderful accomplishment, but it was really just the entree to get the workshop back into control. Workshop had a long history of control, but it hadn't been doing a lot of control for the previous decade. And now we're trying to get back into that. And the reason for that, for this whole Learning to Race challenge this year, which basically consists of, I'll show you what it is, but here it's actually running. I don't know if you see the animated GIF. There's a little car running around here, mostly driving off the track. The idea of this challenge is that learning to control dynamical systems is a hot topic. And you know, for example, there's a conference at Berkeley just last year, just a few weeks ago, learning for dynamics and control. The first year, I think they had 400 people. This year, they had many, many more people. So machine learning and control are coming together. It used to be that control was dominated by feature engineering. People were control experts and developed complex models of control systems and then developed controllers to control them. And now, you know, maybe there's a trend towards becoming more data-driven. And so we want to explore that. We're basically beginners at that, but we want to explore this in the context of this racing game. So we will explore it in a simple virtual racetrack where contestants duke it out using their software agent. The cars will have unknown and complex dynamics, actually more complex than you might think, on a known track which has unknown traction. Contestants will get full state information, so from the eye of God, so no need for fancy perception or slam, and they'll use it to learn how to control the cars to win, a time trial or a race. Data collection will be real time, so you can't do any accelerated transfer learning tricks, but can use end-to-end human data. In other words, you can collect data by driving the cars around the track yourself. And from that data, you can extract the dynamics, hopefully by some interesting algorithm, and then do control with it, like model predictive control or some kind of optimal control. This will be a pure Python machine learning contest of the best control learning algorithm. And so the people that are putting this together are myself and Marcin Paluch, who's just before a PhD, Antonio Rios from Alejandro Linares' lab in Sevilla. We've had technical assistance from Moritz Klischat and Matthias Althoff, who are real experts on car dynamics at TU Munich. And also Chang Gao will contribute his expertise on training RNNs. And Mike Berechtin has now set up a cloud server machine to run on a model server. So people can run their cars on the model server. That's attached to a high bandwidth cloud connection. So the aim of this L2 race, as I said, is that you must develop an algorithm or network that learns to drive the car around the racetrack. You get only limited real-time data from trial runs. You're not allowed to look at the car dynamics model. So the challenge will run the model on a remote server. And so you're not actually allowed to get any model parameters, even the structure of the model, although you can certainly surmise what it might be, but we might change it on you. And you get complete and perfect state, so you don't need to do any perception. And we set up a whole bunch of tracks already to play on. There's a very easy starter track. You just start the track with an option name, and you have all these other tracks that you can play around on. So go for it. You know, that's all I'm going to say right now, except that we'll do it. Get out your joystick controller, or you can use a keyboard and start collecting data. And just this morning, we had a breakthrough because we finally managed to two cars against each other. Here you see Marcin and Chang, both remotely from the server, running these cars against each other on this racetrack. And now perhaps you can do a demo, Marcin. And by the way, I forgot to say that Rachel has joined us from Caltech today. I don't know if you're there, Rachel. Are you there? Okay, so do you guys want to run the demo now? I think you have to make Marcin the host, a co-host.
We can run it.
In the meantime, while they get going, I'll just take any quick question that anybody might have.
Can I share my screen or no?
But okay.
Yeah, go ahead and try to share your screen. I'll stop my share here.
No, I still do not have permission for that.
Okay, I have to find him. Okay.
Okay, so now what Marcin is going to try to do, I'll describe what he's doing.
You are now a co-host.
Great, thanks
Yep.
a lot. Sure. Okay, so that is our.
And Chang is there too, right?
Yes, he is there. I don't know, not
In spirit, at least he's somewhere connected from his apartment. He's controlling one of those cars, and Marcin is controlling the green one here.
exactly. Yes, the other
So-
car always got black.
Ready,
White.
set, go.
Ah,
Losing man. Okay, you see, actually, when the car hits the yellow part, it's kind of like going into sand. You see how he got stuck there? And now he disappeared. Oh, he went back to the start. He reset. He decided to go back to the beginning instead of trying to get out unstuck from the sand. All right, Marcin is already half a lap ahead, but Chang is quickly catching up. And now you have to realize that while people, yeah, you're getting your butt kicked. Anyway, right now the cars cannot collide with each other, but anytime you're actually doing a race like that, all the data is recorded out, all the sensor data, the control data, the state, complete state is recorded out. So now you can use that to attempt to train your dynamical systems model and, go for it. Just try to do control. Thank you very much. So do you have any questions or any discussion about that? Thanks a lot. That was cool. It actually worked.
thanks a lot.
Yeah. I'll just finish, I think, with the last slide. By the way, I already shared these slides. I think a lot of people in the group. Can you see this? So the software setup is you go to the channel. We have a repo. Right now, the version that you'll get is like the master branch. What they demoed was the develop branch that we just got working. If you're interested, take our poll. We have a Google poll that will tell us something about you and about your background. And what we've learned from this is that in the people that took the poll generally consider themselves Python savants. They have a high expertise in Python. They don't know very much about control. They consider themselves kind of beginners in control engineering. They also know even less about car dynamics. There's a few people that claim they know something about car dynamics. But do consider themselves quite expert in machine learning, right? The people that register for the poll. And little of them, almost none of them have any experience with any kind of simulation or real car racing. So we're kind of starting from way behind, the expertise that people come to who get involved in Formula 1/10 challenge or something like that, where they've worked with robot cars, but we will try to bring a fresh take to it that tries to depart a bit from the millions and millions of trials that people do for reinforcement learning experiments now. That's the main aim. Any questions?
Okay.
Okay, post your
Just like-
questions to us on the L2 Race channel. Thank you.
Okay, so I'm gonna be next. Do you see?
Yeah.
Do you see the main screen? Yeah, okay. So this project is about studying the early motion pathway, also called the illusion project. So what I would like, the idea is from what was done in the very early days of vision, from when the vision system, our vision system sees something that isn't exactly there. It's malfunctioning. Can we, from this malfunctioning, understand how the vision system works? That is the global idea with studying illusions from the scientific point of view. And I call it early motion pathway because that's how it's called in neuroscience. In the neurosciences, these processes that are working on the motion early on, starting from the retina over the LGN, V1, V2, and MT. And we know from a computational point that the tasks that are involved are image motion, scene structure, 3D motion, and then there's also tracking. So what's the challenge? The challenge is we want to create programs that predict optical illusions, but under normal conditions, predict correct motion and actually make code available. So illustrated here, you have a new illusion within these motion illusions. You put it through your program, throughout the program that we're going to create, and out comes the prediction. Where the prediction means basically what movement is experienced that isn't actually there, and also the segments, the different parts of the scene that are moving independently. Like here in this pattern, you see a rotary motion, left, right, and then that's what you would. Ideally, that's what we would like. So now, the box is not so black. So it looks a little, because we have been studying illusions before and we have some hypotheses. So that's where we can start with. And I will tell a little bit. So the project is really, we can create a classic algorithm that has this component. I'm interested in neural network implementations that implement a different component. And if someone is interested, we can also go to spiking neural networks. The illusions I have, there are also few, exactly 3, where I have specific tasks to do that are actually not studied yet, where we even can do psychophysics and variations and whatever, publish the first works. So, and this not so black box, is, for example, here, this is also in the video, there's, why is it not playing? This is the Ouchi pattern. And one thing which we strongly believe is the statistical bias. So when there's noise, you do your best estimation, but because of bias, you do not get the veridical. And that actually affects any motion, whether you're moving with your 3D or just moving your eyes. It also affects other things, so it should be a very strong one. A second one is the snake illusion I want to look at, where I have the hypothesis from previous works that it is because of causal flow, meaning when we compute time derivatives, we compute them from the present and the past. So we have a causal filter, and that is responsible for here, and there are many variations. Another one is the so-called Leviant illusion. You see here, if you look at it from a little distance, most people see here rotary motion in these circles. And I've created variations of it. This was actually quite a while ago. Here you probably see the same. And the hypothesis, what I did with the stimuli is they are somehow reduced. You wouldn't be able to get your own ego motion. And there's a theory that it's really feedback from this 3D motion, the main cause why you see it. And then the third illusion that's interesting for event-based processing, the stepping feet illusion, where when this parallel square moves over because we think of contrast, which is very weak and which is exactly what we have in event-based processing, asynchronous processing, you do get also erroneous segmentation and motion. So what will be the roadmap? We are for this program of studying illusion. I believe we can add it in one by one. So if we just start modeling with our classic modeling or neural network models, write good code that predicts image motion, we will already get bias and be able to predict illusions like Ouchi. And there are many more. If we also add in segmentation and fixational eye movements, the drifts and causality in it now, then we will be able to, I think so, we were trying to get onto the snake illusion. And then to fully model this is actually depends on the resolution of the eye. So because when you fixate at the point where you have very high resolution, for example, you don't see this illusion, you would have to model this completely. So also something like a log polar, but not in the first stage, in the second stage. Then we can add in our loop of image motion segmentation, which you start with image motion. From there, you probably get the early segmentation, you estimate 3D motion, which could be your eye movements if you're sitting still. And then you go back and do better segmentation, is the hypothesis. So if we add in full 3D motion model also, we should get illusions like this. And then if we add in also the asynchronicity, we should be able to get onto the stepping feet illusions. So this is the road plan, and we have started a GitHub site which I made the information available on the video and also on the Vision channel. Yep, and so this concludes my project. Description.
Thanks, Cornelia.
That's very nice,
Cool.
Cornelia. Thank you.
And do you have any questions now and posted in the questions channel right now?
Okay, actually I started the first meeting. I had it announced already yesterday, which is okay, but everybody can, we have started summarizing what's in the meeting. I will send out, please everybody really in the Vision channel say whether you're interested in, and since I'm going away a few days, our next meeting is Wednesday.
By the way, we should say that all these meetings will be arranged through the Slack channels, and they'll be put onto the calendar, without disclosing any information. Just the fact that these meetings will happen will be put onto the calendar, and but we won't put the Zoom links on the calendar because we don't want to be Zoom bombed. But we'll put the fact that we have these meetings onto the Google Calendar, and then it'll be easy for you to see when they're occurring. Because we're going to need a lot of these to discuss things with the people that are working on the projects.
And you will put what you're saying, you put the links in the Slack channel.
The links, the Zoom meeting rooms will be put on the Slack, but not, but the fact of the meetings will be put, the times, the scheduling of the meetings will be used the Google Calendar to choose, so make it easy for you to, to see when they're taking place. Okay. That's the plan anyway. Does that make sense?
Yes.
Okay.
Okay, so our next speaker is Terry.
Right. Someone will have to make me co-host so I can share my slides.
Okay, 1 second. You are.
Hey. Come on. All right. What do I have to say? I think the main thing that I wanted, so There was a bunch of different talks that we saw over this week that came around the topics of reinforcement learning and one-shot learning and few-shot learning, recurrent neural networks, and learning in those sorts of domains. And that's sort of the general picture that I want to be doing for this sort of project. The things that were coming to mind for me, we saw some neat examples of using recurrent networks and training recurrent networks to do particular tasks. There was a really good one of the Pong example. There's a whole library of other sorts of reinforcement learning tasks through the OpenAI gym. And I think there's been a lot of interest people have expressed in terms of, hey, let's just start by replicating some of those and starting to like mix and match between these things. So I have a bias towards these Legendre memory units that I was talking about. What happens if we compare these things? A big part of that for me is I just want to get some experience working with these other models and implementing them and getting a feel for them. So that sort of is sort of an initial step of, hey, okay, these are the things that are out there. Let's try implementing them and playing with them a little bit. And then to direct the playing with it a little bit, I've been enjoying reading a bunch of papers lately. Oh, whoops, my slides are out of order. I've been enjoying reading a bunch of papers recently about guided reinforcement learning and imitation learning, and just these sorts of ideas of taking a reinforcement learning system and supplementing a bit of knowledge, adding in a bit of things. So the imitation learning ends up being pretty straightforward of sort of, here's some examples of good behavior. The guided reinforcement learning is a much sort of broader sense of helping out a reinforcement learning system in different ways. This particular paper is an example of actually just giving, verbal descriptions of what it's doing and having that help out. So those, to me, those are all sort of like things to do once we've got a sort of a sense of here's an initial thing working, and then if we want to go, do replicating something that already exists, these sorts of networks that we've already talked about this week, and now let's work in these directions of, can we get them to learn faster by giving them supplementary information. There was also another direction from Andreas Stocko's talk, and it was actually a big part of why we invited him, is these ideas of reinforcement learning in biology has a few different features that aren't common in traditional reinforcement learning algorithms, in particular this go-no-go sort of things, that you're both learning whether to do an action and whether not to do an action, and that these can be thought of as separate systems or separate parts of the same system. And so bringing those in as well sounds like a fun project to me. In addition to that, I've been having a lot of fun over the last month playing around with the recent development in natural language processing that sort of hasn't been talked about so far at Telluride, but the GPT-3 model that was released a few months ago, and all it is just a sort of a natural language processing. Here's a bunch of text, please predict what comes next. But it turns out that it's so successful at that task that it ends up being a few-shot learner. It ends up being something that you can give it a few examples of a task and it will generalize in at least some cases. And it's still not clear yet exactly what cases that works and what cases that doesn't. But it feels to me like a really interesting opportunity to try using that with the reinforcement learning, and can the sort of few-shot learning that GPT-3 is doing help in reinforcement learning tasks. Because it's a little surprising that a network that was just trained up to, here's some text, predict what comes next, is able to do tasks like, I give it the text, please unscramble the following letters into a word and please write that word, and then I give it some scrambled letters and it comes back with the word in the right order. That's a sort of a surprising thing for these network, that a network that is just trained to predict the future or predict the next text is able to do that. So it feels like it's at least something that I would like to also play around with, and fits within the framework of this project. Finally, there's been a bunch of random questions about Nengo in particular, and since I spend all my time playing around with Nengo in general. And I want Nengo to be accessible to lots and lots of different sorts of projects and not just be about the neural engineering framework stuff that I do. There's been, I tend to also like having sort of side projects that are just sort of apply Nengo to different situations. And there's been some interest in projects of, hey, let's just connect it up to whatever robots you happen to have lying around. I have a bunch of Lego robots lying around. People have some quadcopters. Let's go ahead and do that. And then there's also been a nice suggestion of, hey, can we connect something as high level as Nengo down to something as low level as Spice and do some sort of, can we do, can we sort of explore, okay, what sorts of things, if as you change features at the very, very low levels of your very neuromorphic neuron circuit, how does that affect what a network of these things might be able to do? So I think projects like that and any other projects where people have this sort of weird, crazy idea, I also like doing those sorts of things, even if they don't fit perfectly within the mandate of this project. Okay, so that's the sort of general overview. I think the starting point is very much the let's go dig into these existing papers, replicate them, and build up from there. But then I want to go see where people's interests are to go and continue that. Thanks. Any questions from all of that?
All right, thank you. Questions?
There's actually one general question from the questions channel, which is, can we participate in multiple?
Microphone, Amray. Your microphone boom is up.
I don't know why it's doing that. Okay, is that better?
Yes.
Yeah.
Okay. So a question from the channel is that, can we participate in multiple challenges at once? And the answer is yes, of course. And in fact, for example, in Terry's challenge, I can see a lot of points in common with the metal challenge and other pairwise, as well as with Toby's.
Yeah.
Okay.
Yeah, thanks. Do you want to sum up, Cornelia? I think we went during the workshop. I think at the start of the workshop, we were about, what was it, like 600 people registered? I can't remember now. Now it's like thousands. So we got like 400 people. I don't know how many active, but isn't the Slack group having like 500 people on it? The Slack workspace? I don't know how to get the number of people.
Wow,
But yeah, it's
that's
really cool.
exciting.
Active chatters, we've had over 1,000 people join us on the Zoom, and we've got hundreds of people interested in the challenges at a minimum. So I would say
there's 500 people on the Slack right now.
Oh, by the way, you should summarize one more time. I'll just share the screen here. I just want to summarize for everybody that's participating here how it's going to work over this period. So we have this program of the workshop. And now we just finished these first 5 days of the workshop. Can you see here? We finished the first 5 days. Now we're going to work on these challenges during this coming, roughly 1, 2, 3, 4.5 weeks. And then we're going to get together again on September 10, 11 in a similar couple of 2-hour sessions. And then please join and you'll see all the actual results, what people manage to achieve in these challenges. It'll be really cool to see what we can get done during that time. So that's the plan, and all this stuff will be happening. I assume the challenges will be meeting a couple times a week or chatting more or less continuously. People will drop out. We may recruit other experts. It's going to be quite cool, and it'll be quite different than the usual Telluride thing. So we're very curious how it works out.
Yeah, and in terms of outcomes, could be really exciting demos. It could be publications. One of the things that always gets everyone very excited about Telluride is when we have these, communities that come together. Maybe people who've never worked together before, maybe across 5, 6, 7 different institutional boundaries, but then publishing work and kind of demonstrating the value of bringing you all together for these types of things. So we hope that you get not only, some new knowledge and some new experience with some cool tools, but we also hope that you meet some new friends, make some new collaborators, and maybe advance science in ways that never would have been possible.
So Toby, I don't think it's quite fair to say that the Telluride experience was the end. When you leave Telluride, it stopped because, as you know, collaborations kept going, projects, and so this, I think,
camping trips.
Yeah, camping, you know, all sorts of ways for people to keep working together that started, you know, was a starter environment.
Yeah.
So it'll be interesting to compare, but I think that already there was a tradition, a long tradition.
Yeah, thanks, Terry. Yeah, I always feel this at the last day, and I'm sure I share this feeling with the rest of you who have been in Telluride after this 3 weeks of intense like work holiday. I always feel quite depressed for a day or two. I feel like kind of let down. As soon as everybody leaves the town, I feel like it's just empty. You know, I've lost my connection to it, and just it's really a unique experience. I feel so grateful that we've had this opportunity the last
that is true, and
decades.
Yeah. I feel the same way. I mean,
and I don't think, I don't know other communities, maybe Woods Hole or, you know, Cold Spring Harbor, but for sure, the technology communities don't seem to have this as much, like robotics and for sure not electronics.
One thing I'll point out is that, you know, we are absolutely charting a path forward for the Telluride workshop deep into the future. And so, you know, while this year was obviously a strange interruption in terms of our ability to gather in person and work together, that will return. We will definitely bring that back. And I think one of the really exciting things that we're going to get out of this year is that we're going to get some exposure to hundreds of new research scientists that we never would have had a chance to work with in the past. And so maybe some of you will use this next month of collaborative work as a springboard to make your pitch for why you can help us, you know, come to Telluride with us next year and make this workshop fantastic.
And with these online work groups, we'll figure out what else we can do to Telluride, to the in-person Telluride, to really enhance the participation. So it is really an experiment that we're doing now, and I hope it really works out.
Yep.
Absolutely. I'm sure I speak for a lot of people that we all appreciate all the work you did putting this together and making it happen in spite of this COVID virus going around. This has been phenomenal that you pulled in this many people for this event. And if there's some way you can keep this going in parallel with your in-person meetings, make it somehow broadcastable while it's happening, when you do get back together, that would be a fantastic opportunity for hundreds of people.
Yeah, we'll look at that. The logistics is not so easy.
Yeah, it must.
I think we're getting really good experience this year, and I'm very optimistic that we'll have better tools for engaging the global community, even when we have an in-person community next year. So yeah,
yes, if I may also suggest in future years, once we go back to the real format, it may be good to have this hybrid model where we can have both the online, I mean the on-site and the online presence, because one thing great this year actually has been that we had 800 or 900 people that actually were able to go and join in, whereas before we had a very selective pool, right, where we had basically to close the door for many people. Yeah.
That's what I was suggesting, Gert, that maybe they can
Yeah,
find a way
we'll
to do
try to do something. We need to figure out how to do that, but I think that's really where we're going.
So we have some data.
Yeah.
So I'm sorry, Shishi, did you want to say something?
Oh no, I said this. This is definitely it gives us a lot of interesting ideas to think about. And in the past years, we had to limit the number of people just because rental prices are so high and we can't afford to pay for all the housing.
Right.
So I think the hybrid is going to work out good.
Yeah, no, I think it's very doable. And let me just give you some data because NeurIPS is going to be all virtual coming up in December. But we've already run the ICML conference earlier in July, early in middle of July, actually. And what was interesting there is they had like 5,000 people that signed up. It was, I think, $100, you know, for faculty and $25 for students. But what the statistics that just came back are very interesting. Even though there are 5,000 people, most people only listen to like 2 or 3 talks, or a few posters. In other words, there's a very different form of engagement. You have much larger numbers, but you have fewer extended, intense kind of impact. but it's, you know, I'm not saying it's good or bad. I'm just saying that, you know, that take that into account when you start planning ahead for how to best bring the online people in so that they can participate beyond just, you know, listening to a few keynote talks.
Yeah, definitely.
I mean, I don't know how it's going to work. I mean, if you took one of these fancy webcams that pans around and made it part of one of the rooms so that people remotely could participate, it might work. But I have a story from Caltech back when I was a grad student in Al Barr's lab. Al Barr had a big graphics lab. He got money from NSF or something to set up this live continuous video stream between Caltech and MIT. So basically they had a conference room that was split in half. Half the conference room was at Caltech, the other half was over at MIT. And the idea was because they had that shared conference room with a live high resolution video stream, I mean, this must have cost a lot of money because, you know, it was a long time ago. You know, you were supposed to increase interaction. Well, you know what happened? Nothing. These people just ignored people on the other side of this invisible wall. It didn't work at all.
MIT thing, right?
It didn't work at all. It was complete failure. So maybe for a continuous project meeting, but for casual interaction, it was hopeless.
Toby, we did the same thing for the Kavli, and Terry knows the Kavli Institute between downtown and the Homewood. And that actually worked out pretty well. I mean, you could get people to interact in these rooms.
Maybe that was a decade later. I don't know.
Yeah. I also think the Zoom the tooling and people's tolerance for it has increased dramatically thanks to COVID. And so we should expect a completely different type of interaction with these tools going forward, regardless of the physical interactions. But, you know, given the bandwidth seen in Telluride, maybe we'll need to make it an event-based camera and we'll just transmit the spikes.
Oh, yeah. Not if you want to see it clearly. Oh, by the way, I'm supposed to stick around now. I have to answer questions about this tutorial. That's my job now. I was going to go have a tequila shot, but now I have to do that.
Okay, so do you want to stop the recording first, Cornelia, before we go to Toby?
And just to wrap up that last conversation, we'll be sending